Okay, so here's where we're picking up for today. Still in section 2.2, which we did some of on Friday. So we're trying to understand how to draw solution sets to equations like this one, particularly equations where there are three variables, right, like this, which is a new concept. Algebra 2 classes in high school don't really address this. So here in the multivariable calculus class we do. Okay, so here's the question I want to propose. We'll see where this is going after we get it done. But what would happen, suppose I knew the set of solutions to that equation. What would happen, though, if I considered a new equation that I get where I replace every x in the existing equation, if I replace every one of those with x plus 1, just erase where it says x and squeeze in x plus 1 instead. What does that do to the solution set? And now the reason we want to answer this question is because hopefully you can see the potential for this. If we can figure out how algebraic manipulations cause geometric manipulations, if we can understand the nature of that relationship between algebraic changes and geometric changes, then we can take a very limited set of equations and surfaces that we do understand and just use that as a starting point and start manipulating algebraically and see what happens to the solutions. And we can draw a lot of conclusions if we can figure out the answer to this question. And then there's other, kind of analogous, what would happen if I replaced every z in the equation with some constant c times z? What would that do? And what would happen if I replaced every y in the equation with negative y? What would that do? Okay, we're going to start with this one, where we're going to replace every x in the equation with x plus 1. And so let me start by asking, what geometrically does that look like just by itself? If I have a point, and if I just add 1 to its x coordinate, well, that's a pretty easy question, right? This process of adding 1 to the x coordinate, it shifts that point by a distance of 1 in the x direction, so that's easy. All right. Okay, so here's the harder question, though. How does that relate to equations? And specifically, we're interested in the equation f of x plus 1, comma y, comma z equals 0. And we want to know, how does that relate to now our original equation, which was just f of x, comma y, comma z equals 0. Okay, so here's the way I want to break this down. Again, let's presume that I know what the set of solutions to this looks like. Suppose that I know that that's some surface S, for example. Right? Remember, I know what this does. This idea of replacing x plus 1, that's going to take wherever I might happen to be. Oh gosh, my elbow hit the thing again. I'm sorry. Wherever I might happen to be, that's going to move by a distance 1 in the x direction. So, what this says here, this says I'm looking for points which, when I move them by a distance of 1 in the x direction, I want the result to be something that when I plug it into the function f, I get 0. Everybody see how that's the interpretation there? I mean, importantly, in this top algebra that I have highlighted in yellow, in that top algebra, we're adding 1 to the x coordinate before we plug into the f function. Right? So a solution to this equation that I have on top is a point that, let me say it again, when I move it by a distance of 1 in the x direction, the result is a point that satisfies the original equation. And now let me say that geometrically. Same statement. I'm just going to say it now geometrically. This yellow equation the solution set is a set of points that when I shift them in the x direction by a distance of 1, I get the original solution set S. Right? So now that being said, I'm looking for, this mystery surface that when I shift it in the positive x direction gives me S. Another way to say that is that this mystery surface is the result of shifting S in the negative x direction. I've got to undo what this adding 1 to the x coordinate does. How are we doing? Is everybody on board with that analysis? Okay. So this is a kind of an interesting result. Let me come down to the little summary page that I have here. What we've concluded, and I did this with shifting by a distance of 1, but it's analogous if your distance is some number c. We've just argued that if you replace x with x plus c, that actually translates the solution set by a distance of negative c in the x direction. Okay. All right. So the broader lesson to take from this is, again, looking at what we have here on this previous page, looking at the way the algebra works out, looking at the fact that it is something that happens to points before you plug them in, right, that makes these seemingly, aren't we kind of adding 1 to the x coordinates? Actually, we're effectively subtracting 1 from the points that are actually solutions. We're subtracting 1 to get points so that when I subsequently add 1, the equation works. Let me say that a little bit differently again. What you do algebraically, what you do to replacing variables algebraically, sort of the opposite happens geometrically. What happens geometrically has to undo, it has to account for what you're doing algebraically. Okay. All right, so let's apply that sort of broad lesson, and here's a bunch of punchlines. Now, analogously, you can persuade yourself without too much trouble if you replace y with y plus c. Well, that's going to translate in the negative by negative c in the y direction, likewise with z's. But same sort of argument. If you replace one of the variables by a constant times that variable, it's you're tempted to say that it would stretch by a factor of c, but no, it does the opposite of that. So it stretches by a factor of 1 over c, or sometimes I like to say it squishes by a factor of c. Terminology. Suit yourself. Again, opposing what happens algebraically. Okay. Now, good news. Replacing a variable with the negative of it. Let's look at, what do I feel like is happening there? Well, I feel like that, when you replace y with its negative, you're reflecting through the xz plane, right? Well, the opposite of a reflection is that same reflection. So there's sort of no opposition here, or said differently, the opposition is itself. Okay. All right. So long list of rules of if you do this algebraically to your equation, then here's what happens to the solution set. And there's powerful conclusions that can come from this. Let's see here. So I'm going to start with a quickie example. Here we go. So let's look at this equation right here. And I claim that that's pretty easily seen to be a sphere centered at the origin. Now, how would I see that this is a sphere centered at the origin? At several different points of view you can take. One thing you can do is take cross sections. Right? We saw how to take cross sections last time. Take cross sections, various slices. Set z equal to various constants, you get a bunch of circles. Set y equal to a bunch of constants, you get a bunch of circles, etc. So this surface is a surface, all of whose cross sections are circles. This kind of has to be a sphere. So that's one way to see it. Another way to see this is that pretty also easy to see. This is just the square of the distance to the origin. And so if we're looking at the set of points whose distance to the origin is exactly 1, okay, that's very clearly a sphere. All right. So what then is the solution set to this equation? This is a different equation here. Solution set to that equation. Well, here's the thing. this brand new equation, it's not the same as the previous one, but it's exactly what you get if you take the original equation and replace the x with an x plus 1. Right? So that algebraic process turns that equation into that equation. I already know geometrically what this green equation looks like. That's a sphere centered at the origin. This yellow replacement, well, I know what that does. I can look it up on the chart. Where'd that chart go? Here it is. Go look it on the chart here. When you replace x with x plus a constant, the result is to translate in the other direction along the x-axis. Where am I? Here we go. So I conclude from that argument that this sphere centered at the origin gets pushed by -1 in the x direction, resulting in hopefully a sphere centered at -1, 0, 0. And now, just as a sanity check, I like this as example, as a starter example, because we have a way of confirming whether or not we're actually correct. And the confirmation comes from rewriting that equation and realizing that what we have on the left-hand side here, that is distance squared to the point -1, 0, 0. Right, so our argument about what happens when you replace variables, we have a confirmation seen from a different point of view. Everybody happy? Okay. Alrighty. Now, I started in this example here with, let's start with a particular surface, and then let's use that to understand a different surface. If it does not come to you in that form, which, by the way, usually won't, here's kind of the same example, but said a little bit differently. Just what's a solution set to that equation? Now, it's the same equation from the last one. But here I'm not telling you, let's start with the following. Right? So your first step in that process then is to ask yourself, okay, looking at that algebra, can I think of some surface whose algebra looks a lot like this, and whose solution set I know? So this is just kind of a strategic sort of thinking about it kind of a deal. Strategically, I notice that the algebra here, these two bits of algebra look a lot alike, and this one is one that I already understand. And then proceed as in the last example. Okay. All right. So now here's a harder version of that same example, same kind of example. What's this? Ooh. So that's significantly different. I'm not replacing y with y plus a constant by itself. Right? I'm not simply replacing y with y times a constant. I'm kind of doing a couple of different things. Nevertheless, it remains, and I hope you have the instinct for this, that we say, look, that looks an awful lot like that algebra right there. And I could probably, you give me a couple of shots at it, come up with a succession of replacements. Let's replace y with, we'll make some decisions about exactly how to do that, and have this algebra here turn into that algebra. And then we can use our knowledge of the relationship to geometry to figure out what the surface is. Okay, so I'm going to start with this surface here, know the equation, I know the solution set. Here it is. That I understand. That equation, that surface. And now, pictures aside, let's pretend that we haven't got this written down, and let's just think about just the algebra. And likewise here, we don't know this picture yet either. Let's just look at the algebra. If I want to get from this algebra, I want to get from that algebra down to this algebra, what replacements should I do? Okay, this is the algebra I understand. This is the algebra I want to understand. What's the algebraic connection between them? Well, this is going to seem a little bit wrong. This is going to seem a little bit backwards, but it is what it is, and it's just kind of has to be. You look at this and you feel like by the order of operations, shouldn't we do the multiplication by 2 first? And let me just point out that it doesn't work that way. It works seemingly backwards. Despite the seeming flaunting of the order of operations here, let's start by replacing y with y minus 1. Let's do that first. There you go. And now, having done that, and I emphasize, having done that, I am now focused on this equation and its mystery surface that we haven't thought through yet. But anyway, looking at this equation, how do I get from that equation to this equation? Ignore what the equation used to be, what it used to look like. This thing has served its purpose. Its purpose was to get me to here, which I now am. I am now looking only at this equation here. And in that equation, what do I do to get this to look like that? And the answer is, I need to replace y with, it seems 2y. Everybody see that? Now, the common mistake happens all the time is students think, well, yeah, but look, I mean, this is kind of sort of y, isn't it? This is the thing that, well, it used to be y, or something like that. Okay, and you got to forget about that, right? Where it came from doesn't matter. Our process involves looking at equations and what happens when you replace a variable in the equation, independent of, don't worry about the fact that, other things didn't used to be there or somehow connected to it. That's not the point. Right? A variable in the equation, and what do you replace it with to get what you're interested in? So there's our next step. Having noticed those steps, and again, seemingly they're backwards, it feels like, shouldn't we do the multiplication before the subtraction? It just feels wrong. Nevertheless, this is what gets you to what you need to get to, and now let's just think through what is the result in the geometry. This step, replace y with y minus 1, is going to move the center. That's going to move the whole sphere, but therefore the center also in the positive y direction by a distance of 1. Positive, because that's the sort of the undoing of that negative. Then, having done that, this process, replacing y with 2y, it's a multiplication by 2. Again, your first instinct is to think that that's going to stretch in the y direction, but again, it's not. It's the opposite. It squishes in the y direction. And so we have some sort of it's called an ellipsoid, right? For a C-section 2.2, yeah.
So for an equation like this with, I guess, like quadratic term or with like squares, if you wanted to reflect it over a plane, could you do anything?
If you take this sphere here, this original sphere, and if you reflect it over what we call a plane of symmetry, or one of the coordinate planes, yeah, it doesn't do anything. So you can see that geometrically, as in a sphere is its own mirror image over that plane. You can see that algebraically in the fact that if you were to replace this z with negative z, algebraically nothing would happen because you're squaring away that minus sign. So take your pick. Oh no! Now over here, if you replace y with negative, if you were to reflect through the xz plane, yeah, that's definitely, you can geometrically see that's going to make a difference. Algebraically, you can see that would make a difference because if you replace this y with negative y, it algebraically changes. Perfect. Yeah. Yep. Absolutely. Okay. Okay. Let's see here. So one last little quickie point. Two last quickie points. One is you could, if you really want to, right? You could do a translation after a squish. That's true. But you would have to adjust the amounts. In other words, if you simply change the order of these, you won't get the right algebra. And if you don't get the right algebra, of course, you don't get the right surface. Right? But if you were to change this if you were to, switch the order of these two operations and replace this with a half, then that would get you down to the right algebra. I just would make the observation that, but why would you want to deal with fractions? Right? Do what's going to be the most convenient. And I think this order that we've got here, I think, is the most convenient. Now, the second observation little quickie observation I want to make is how the squishing works. When you do this, a lot of students think, oh, squish. That's like when I take a soft rubber ball and I kind of push it in. And when you pick up a soft rubber ball and push it in, you always push toward the center of the ball. That's how balls work, right? But that's not what's happening here. What is happening here, very importantly, is all of the y coordinates are getting cut in half. So this is not going to be like you're taking a ball and squishing it and that everything moves in toward the center. That is wrong. What it is, I guess it's more like you have a brick wall over here that is the xz plane, and you are squishing by pushing it toward the brick wall, right? And then all the y coordinates get cut in half in that sort of a squish. So don't make the mistake of thinking, it's a squish. Squishes go toward the center. No, the squish is centered on the coordinate plane. Okay. Alrighty. Okay, so move along. Next section. Here's another tool for you to use. By the way, you'll notice that the big tools that are in section 2.2, these are all somewhat general tools. These are all of the sort of, here's an idea that can be applied broadly. Here's an idea that will allow me to take a simpler problem, something that I already understand, and use that to extrapolate to a harder problem that I have yet to understand. Right? So cross sections had that feature, right? We're figuring out how to use the idea of understanding equations of two variables to interpret those as being cross sections and therefore help me understand equations of three variables, etc. Okay, so here's just another one. This one is arguably less broad. This applies in a narrow set of cases. So here's the narrow set of cases. Let's suppose that my equation fits this form, and most equations don't. This form. That the equation, the thing that equals zero, the expression that is my equation, is a function where x and y appear only as part of that specific expression, square root of x squared plus y squared. Now, again, that's not always the case. Most of the time, this is not true, right? I mean, here's an easy one that denies this rule. X minus y cubed equals z, right? X and y simply do not appear as part of this form. There is no way to do that for this equation. Okay, so only sometimes is this true. Now, here's an example where it does work. That equation right there. X and y appear only as part of our special form. Right, so specifically, let me get rid of our... what you have here is that square root of x squared plus y squared, when you square it, gives you that part of the equation, and the rest of that equation is like that. Okay, so like I say, very narrow. But when this happens, when you get this algebraic good fortune that x and y appear only as part of this very special form, powerful conclusion. And let me take you through a multi-step process to reason through, what that is. First observation, notice that this little magic expression we're talking about, square root of x squared plus y squared, that is the distance to the z-axis. I'm going to call that r sub z. I'm going to just, draw the picture out, think it through. Square root of x squared plus y squared is the distance to the z-axis. What that means then is that our equation is entirely decided without knowing x and y specifically. It's entirely decided only by knowing the distance to the z-axis and z. Let's look at a picture. Here is such a picture. Let me write down our equation. G of rz comma z equals 0. There's that equation. Let's consider a couple of points. This point here that has those coordinates, and now here's another point, totally different point. This point here that has those coordinates, they have different coordinates. They're not the same point. They have different x's. They have different y's. But as drawn, this being a rotationally symmetric surface, these 2 points have the same distance to the z-axis. They have the same z, right? So same z, same distance to the z-axis. That means that these 2 points, the orange point and the red point, either they both work in the equation and therefore they're both on the surface, or they both don't work in the equation and therefore are both not on the surface. So this is the picture to have in mind to make the simple conclusion that if you have an equation of this form, you have an equation of that form, where again x and y appear only as part of the special form, your surface is rotationally symmetric around the z-axis. How are we doing? This is a powerful conclusion, geometric conclusion to draw just by virtue of what I'm going to call an observation about the algebra. Quick observation about the algebra, and you know something tremendously strong about your surface. Okay, now here's how you can capitalize on that. It's just a quick observation, second observation about rotationally symmetric surfaces. If a surface is indeed rotationally symmetric around, let's say, the z-axis, I innocently point out that if you were to then look at a half plane hinged, I like to call it hinged on the z-axis. In other words, this half plane's sort of boundary line is on the z-axis. If you have a half plane hinged on the z-axis, and if you were to look at the cross-section of the surface in that half plane, now don't forget our premise is that this surface is rotationally symmetric. This cross-section, if you were to rotate that cross-section around the z-axis, it would sweep out the entire surface. That's just a geometric appeal, right? That's what it means to be rotationally symmetric. Okay, so now let me summarize what we have. We've got it down now to if we notice a certain convenient algebraic feature, then I can take a particularly chosen curve. That's a curve inside of a half plane. I understand curves inside of planes. That's Algebra 2 stuff. I can take a simple curve that I can understand from the Algebra 2 point of view and then just geometrically ask, okay, yeah, and let's rotate around an axis and just think about what that looks like. This is lining up really nice. Right? Okay. Last little detail. What is this curve? Well, this curve is what you get when you take your equation and cross-section with a half plane. Let me remind you what a half plane is. A half plane, in this, now let's look at this particular one arbitrarily. That half plane is described by, well, y equals 0. Right? But now, very importantly, you'll see why in a moment. I do want to constrain myself to just the half plane. I do not want to allow all of that stuff over there. Because I don't need it, for one thing, right? Just from a rotation argument, anything that's on the other side of the plane, I'm going to rotate into that. So I don't need to have it, and it's also going to turn out, you'll see momentarily, that it's very problematic to leave it there, right? So I need to figure out algebraically how can I jettison all of this junk over here, well, on the other side of the half plane, and here's a really easy way to do it. I'm just going to say, let's look at the part where x is non-negative, and then that disappears. So this is the algebraic description of that half plane, and there's a nice punchline here, and that is, given that half plane, if we look at our little magic expression, square root of x squared plus y squared, well, if y is equal to 0, that gives me square root of x squared, and a lot of people spike the football here. That's premature. This is it's tempting to call that x, but very importantly, remember, that's not x. It is only because x is assumed to be positive, because we have made the clever choice to jettison this other half of the plane, and therefore we get to say x is positive. Only because of that can I lose that absolute values and declare this to be x. Yeah? How are we doing? Okay, again, let's sort of hit the highlights, summarize, what have we got? Notice something about the algebra. Notice that x and y appear only as part of the special form. As a result, my surface is symmetric. I know that my surface is traced out by this curve. This curve is what I get by constraining myself to a half plane, and in that half plane, this magic expression simplifies wonderfully. It's just x. Okay, so here's our theorem, and then we'll do an example. If you have an equation that fits this form, where again x and y appear only in that way, strictly only in that way. If that happens, then just look at the surface that you get in the xz plane, defined by replacing square root of x squared plus y squared by x. And don't forget the critical inequality. X has to be positive, so in other words, only look in that half plane. Take that resulting curve, rotate it around the z-axis, and there's your surface. That's it. Okay, so let's do an example. Now, the purpose of this first example, this again is a sanity check. I love sanity checks. What I mean by sanity check here is, let's confess, we do already know the answer to this question. This is z equals x squared plus y squared. We talked about this one last time. This is a paraboloid. Right? This is the first surface that we looked at by looking at cross sections. We had all these cross sections in different directions, and we thought about it from these various different points of view of cross sections and reassembled these curves in our minds into a surface. It was pretty geometrically challenging, and came up with that is a paraboloid. Okay. Now let me show you the alternative. Easier way to do it using a rotations argument. I quickly observe x and y appear only in that special form. I know this is rotationally symmetric around the z-axis. Pick any half plane you like. I'm going to pick the one that we were just talking about, in which I can get rid of all of that, replace it with just this. Now here, the fact that x is positive didn't end up mattering, coincidentally, in this case. What possibly could have been an absolute value sort of disappears when you square, so it doesn't matter in this case. It will matter sometimes. Anyway, the point is, all I have to do is look at that equation. That's an easy equation. That's a parabola. I just need to look at that parabola, look at the part in the xz plane where x is positive, and I just need to rotate it. And this is easy algebra. Let's see here. Here we go. Here's the xz plane. Remember, we are very critically getting rid of all the stuff on that other side. So I only want to look at the part of the xz plane with x positive. So just this part over here. That parabola, z equals x squared. That's easy. Z equals x squared is that. Oh, wait, no, don't make that mistake. It's just the part where x is positive, right? And take that curve, rotate it around the z-axis, bam, paraboloid. And we don't have to take a million cross sections. We only have to take one cross section. How are we doing? Okay. This is a nice, really nice tool. Saves you a bunch of trouble in a lot of cases. Now, I do want to give you one more example. This is a harder example. This is one that would be, I guess you could do this with cross sections, but it's going to be significantly more challenging. Let's look at this one right here. First observation, x and y appear only as part of the special form. There's no stray x's. There's no stray y's. There's not like an e to the y hanging out somewhere, right? X and y appear only as part of the special form. I quote my theorem. This is rotationally symmetric around the z-axis. I just need to look at the cross-section in a half plane. In that half plane, square root of x squared plus y squared is x. So this equation becomes that equation, otherwise known as that equation. So in the appropriate half plane, I just need to understand x equals 1 minus z squared. Now, it's a little different here. I mean, we're kind of accustomed to up being a function of sideways, right? So this is the other way around. X, sideways, is a function of the up variable. So you got to think it through. Here, x being 1 minus z squared, and what we get is in the xz plane, we get a paraboloid that looks like that. Very importantly, we only look at the part where x is positive. Just where x is positive. Over here, in that area, in that region over there, the square root of x squared plus y squared is not equal to x. Over there, x is negative. Square root of x squared plus y squared can't be a negative. It's algebraically wrong if you look at this piece of curve there, sort of the extension where x is negative. That is not, in that region, it's simply false to say that square root of x squared plus y squared is equal to x. It's not. Don't look at that part of the curve. Is everybody on board? Everybody see the argument there? Yeah. Okay, so restricting our attention just to the appropriate part of the curve, we get that little kind of C-shaped little sideways U, whatever you want to call it. Rotate that around the z-axis, and we get a football. I don't know. Anyway, football. There you go. Everybody on board? Alrighty. More examples. I'm going to go more quickly with these next couple of examples because they're kind of repetitive. These are very, very similar to what we've talked about before. So this one, here you go. That algebra, lucky break. X and Y appear only in the special form. This is rotationally symmetric. I can look in a half plane and rotate. Right? Okay, cool. In that half plane, x squared plus y squared is just x squared. So I need to understand this algebra. Now here I will observe that this is a flashback to Algebra 2. A lot of students are iffy on hyperbolas. And there's always this question of, oh gosh, does it go? Is it one of these hyperbolas, right? Or is it one of these hyperbolas? Does it open up to the sides, or does it open up top and bottom? Which way does it go? And look, you can memorize your way through that, I suppose, but I don't recommend memorizing your way through things. It's a matter of time till you forget it, or at least it's a matter of time until you get to the point where you're unreliable with being able to remember it. Right? So I would encourage you to sort of reason your way through it. Here's the way I think of it. Looking at the hyperbola, let's see here, x squared minus z squared equals 1. Between these two variables, x and z, which one of those variables could possibly be 0? I think this is a real easy way to distinguish between the two cases. And I'll make the observation, there's no way x could be 0 here. Right? If you were to say x equals 0, you've got a negative of a perfect square equaling a positive 1. And that's never going to happen. Right? Okay, so what we know is that x can never be 0. And that distinguishes between these two cases. Let's see, where's my picture of this? Yeah, here we go. In this plane, in the xz plane, this is the hyperbola where x is never 0. Right? It can't go the other way. If the hyperbola went like that, we'd be saying x could be 0, which it can't. Right? So anyway, that's the way I think it through as to which way the axis goes. So that's what the cross section looks like. Again, keep in mind we throw away the part where x is negative. X can't be negative if we want to make the algebraic replacement that we did. So this is the piece of the hyperbola that matters. And take that and rotate it around the z-axis, and you get this picture here of, I don't know what to call that. I don't know what to relate that to in sort of real life. Corset? Maybe it's a corset. Very obscure reference. But anyway, this is called a hyperboloid. This is the name that mathematicians use to describe this shape. Hyperboloid of one sheet. And there's a hyperboloid of two sheets that we're going to see momentarily. Okay, let's see that hyperboloid of two sheets. Let's look at this equation. Now, a pretty similar argument. By the way, the x squared plus y squared won't always jump off the page at you. Sometimes it will be a little bit hidden. Here, notice that algebra I could rewrite as negative of x squared plus y squared. Right? And sure enough, x and y appear only as part of that special form. Right? So, this is allowable. This is fine. Okay, so rotational argument, resulting hyperbola, you get this, and again, think it through. The algebra 2 in this case is that in this plane, the hyperbola is this one. That's the hyperbola in that plane. Don't ever forget, it's very important, we're only going to look at the part of that hyperbola where x is positive. Right, so just that part. That's what we rotate around the z-axis, and leave it to your geometric intuition. You take these two sort of parts of a hyperbola, rotate, and you get these two. This is the surface I like to think of as the staring contest. I see two eyeballs looking right at each other. So a couple of contact lenses, maybe. Anyway. So this is called a hyperboloid of two sheets. All right, everybody on board? Okay. Here are some related results. Let's suppose that instead of x and y appearing only in the special form, suppose that y and z appear only in the special form. Analogous argument. I'm going to leave this as an exercise for you all to do. This be a healthy and productive exercise. Think through all the details. Square root of y squared plus z squared is distance to the x-axis. This surface is going to be rotationally symmetric around the x-axis, which means now pick a half plane hinged on the x-axis. Think about how you describe that algebraically, blah, blah, blah. And punchline is there is a corresponding curve that you can rotate around that x-axis to get your surface. Okay. And then likewise, if x and z appear only in the special form, then you have symmetry around the y-axis. Okay, so there's some examples in the rest of this section on that as well. Okay. Okie dokie. So moving along. Let's see, how are we on time? Okay. Okay, so I want to start talking about different ways to understand functions geometrically. And I emphasize in the last section, we've been talking exclusively about equations. Here's an equation of three variables. What's the solution set look like? What are different tools that I can use for understanding solution sets to equations, right? Our focus has been on equations. We're now going to shift our focus to functions, right? The question is going to be, if I have a function, how can I draw a picture that in some way helps me understand this function? I want pictures to help me understand functions. Okay, so the first one we're going to talk about is the graph, and this is largely ancient history. Y'all have done graphs before. What I am not entirely sure of is if you are aware what you've done a million times before is actually part of the graph construction. What specifically is part of the graph construction as opposed to, well, that's just how you do it. Right, so I want to break this down precisely. Okay, so here we'll start off with the following function. Here is a function from R1 to R1. Here's the formula, f of x is equal to x plus 1. This is what we call a single variable function. Okay, y'all remember this kind of a function? And a quick observation I'll make about this function, f of x equals x plus 1. Now y'all have done with this a million. Y'all have drawn pictures representing this function. But notice, as this function is defined, there's only one variable. There's no y. F of x is equal to x plus 1. You give me some input value. Here's a formula for how to compute my output value. I have a name for this output value. The output value is called f of x. I don't know what you're talking about with y. There is no y. Second thing, there's no two-dimensional axis system involved in how I'm describing this function. I've got a domain. My domain is R1. That's not two-dimensional. I have a target. Right? That's R1. That's not two-dimensional. There's no two-dimensional axis system. There's no XY plane. There's no Y. Taking it further. Okay, so we are starting with just the function. Now, what I'm about to do from here is called the graph construction. So there's a particular process that I'm going to now apply to this single variable function. Everything that follows is, it's not just what you do. It's not what the function really is. It's specifically, what I'm going to describe going forward here is the graph construction. And here it is. What you do in the graph construction is introduce a new variable, and we're going to use the y arbitrarily. No particular reason. That's conventional, of course. So pick a variable name. Next, part of the graph construction, set that new variable that you just made up. Set that equal to the value of the function. Now, that's a choice. There is no law that says that when you come up with a new name for a variable that's going to relate to the question in some way, that you are, required to set that equal to the output value of the function. That is a choice. That is part of our graph construction, is to choose to set the output value of the function equal to this new variable. Okay. And then lastly, now that you have an equation, we look at the solution set to that equation. All right, so this is a multi-step process of choices that are completely unrequired if you're not. This is all part of the graph construction. Okay. All right. Now, I hope that looks familiar. And here's an easy example. Let's play that game for this function, f of x equals 1 minus x. Step 1, I'm going to introduce a new variable called y. Right. Step 2, I'm going to set the function equal to that new variable y, thus giving me this equation, y is equal to 1 minus x. Step 3, I'm going to try to understand what is the set of solutions to that equation, which, you may prefer to write like that. Suit yourself, algebraically, those are identical. So x plus y equals 1, and, well, There you go. So this picture here is the result of the graph construction. This is not a picture of the function. This is the graph of the function. This is one geometric object that you can create. We're going to create many other kinds of geometric objects to help represent functions. So this one is not, exclusively the function. This is just a point of view on the function. Okay. All right, I think I've hit that hard enough. Now let's look at a multivariable example. And multivariable is really we're just going to rip off the same process. Notice if I have a function from Rn to Rm, right? Well, there are n input variables. Right? In input variables. There are going to be m outputs. I haven't got names for these m outputs yet. They're just outputs. But I can choose to come up with new names, y1 through ym, set those output values equal to the output values of the function. Now I have an equation, and I can look at the solution set to that equation. So same process, really. Let's apply this to a function from R2 to R1. Here we go. Here is a function from R2 to R1. Notice 2 input variables, 1 output. Let's set that output equal to the value of a new variable. The resulting equation is this. Let's look at the solution set to that equation. Y equals x1 plus x2. By the way, the variables won't always be x, y, z. Right? Sometimes it'll be p, q, r. Sometimes it'll be k, l, alpha. Right, whatever. I deliberately chose sort of non-standard names for these variables. Just I want everyone to be prepared for don't have an alphabetical reliance on certain choices. In other words. Okay. So this plane though, y equals x1 plus x2. Here's a picture of it. It's sort of going up like that. You can see it goes through the origin. If x1 and x2 are both 0, so is y. And then as x2 increases, so does y. And as x1 increases, so does y. So this plane, it's kind of hard to draw a picture just because of the angle and the perspective. But this plane's kind of coming up out of the page. It's going up as it comes out at us. Okay. All right. So that plane is the graph of this function. Again, it's not the function, it's the graph of the function. Okay. All right, here's another nice example. This one's a little bit less algebraically convenient, but let's look at this function here from R2 to R1. That formula, x squared plus y. That's not a typo. I didn't mean y squared. This is f of xy equals x squared plus y. All right, well, the graph is what you get when you set the value of that function equal to a new variable. Now here x and y are input variables, so the new variable I'm going to choose can't be x or y. So I'm going to choose z. Again, why not? Now we have this equation of the graph, and we have a little algebra problem on our hands now. Right? The question of how do I know what the set of solutions to this equation is. This is a section 2.2 problem. And what are we going to do about this? Is this rotationally symmetric around anything? Sadly, no. Again, most of the time, right? Most of the time it won't be, but surprisingly often it is. But anyway, in this case, it's just not rotationally symmetric around anything. Does this look sort of reminiscent of a surface that we already know that we could, maybe by translations or reflections or stretches or something like that, could we stretch out a known surface and make it look like this? And not really. I mean, there is this. It's almost as if there was a square there, but that's not a simple stretch. Right? So no, there's really nothing we can do to recognize this from something previous. So we're going to have to look at cross sections on this. And the way I'd like to look at cross sections is to think about let's set y equal to various constants. Right? If you set y equal to various constants, in other words, if you look at cross sections perpendicular to the y-axis, that's what it means to set y equal to various constants. Set y equal to various constants, the resulting curve is a parabola. Z equals x squared plus a constant. So you get parabolas. Furthermore, notice that the amount that z is shifted up is equal to the y-coordinate where you're taking the cross-section. And so the further you go over, the further your parabola is shifted up. This picture it's not to scale, I guess. I didn't do a good job on but you can see that certainly in the way I drew it, the more you go to the right, the more it goes up. Right? And so that helps you see that your surface looks like this. It's like an angled trough. How we doing? Okay, so now keep in mind we just spent 2 minutes talking about how to understand this equation. That's not really what we were here for. The purpose of this problem was not to understand an equation. The purpose of this problem was to answer the question of what is the graph of this function. And so the graph of that function is that surface. Yeah.
Why does that not go through the origin?
Poor drawing.
Okay.
Yep, it's all right. It's harder than it looks. Yeah. No, I did this drawing back before I had a laptop with a stylus, and could, what I would do now if I were doing this drawing over again is I'm just showing off at this point, but we have a second. I would look at this thing, and then I would say, I don't think that looks just right, so I'm going to grab that and just kind of, hey, there we go, how about that? And, right, but I didn't have that tool back in 2009 when I drew this picture. Yeah, okay. Alrighty. Okay, so I'm going to let y'all read that next example. Now, before we move on, I do want to take a pot shot at graphs. I've made this, y'all probably picked up on my vibe already, but graphs are not all they're cracked up to be in single variable calculus classes. In single variable calculus classes, they have a monopoly on how we understand functions in single variable calculus. We always draw the graph. It's so exclusive. Again, I've made this observation before. The students don't even realize that they're doing a graph. That's just, and a lot of students find that's just what the function looks like, right? So that is an oversell. Graphs are really good, but they are not good enough in a multivariable calculus setting. And so just a really quick and easy example. Let's look at this innocent little function, R2 to R2, right? I won't write down a formula, whatever. Doesn't matter what the function is. But if your function goes from R2 to R2, it's just two variables. It's just barely bigger than 1. This is barely multivariable. And yet let's count total variables. You have 2 input variables, you have 2 output variables. If you're going to play the rules and give names to the output variables and create an axis system that has all of the variables on it, you're going to need to come up with a way to draw a 4-dimensional axis system, and we just can't do that. We are 3-dimensional critters. And can't deal with it, right? So we pretty much can't even visualize what the graph of an innocent little function like this would look like. So graphs have very limited. Look, they're useful. I don't intend to trash graphs. They are useful, but they are far from good enough. Everybody see what I'm talking about? We need to understand functions like that too. All right, so graphs are one tool of many, and let's now go on and talk about the next one. So that's level sets. Okay, so this is another construction, another process where we're going to start with, suppose I have a function. I'm going to make certain choices, do certain things, set this equal to that. I mean, do some sort of algebraic song and dance, and then eventually I will be drawing a picture. Right? So this is a different process by which we take a function and result in a picture. You've got to make a point in your mind of distinguishing between the process of creating level sets and the process of taking graphs. Because the processes are so different, what you can understand about the conclusions are super different. Algebraic features of graphs are not the same as algebraic features of level sets. The calculus of graphs is going to be very, very different from the calculus of level sets. Okay, so now is the time that you want to start building a little mental wall in your mind between, look, graphs, okay, there's a whole story about what multivariable calculus looks like in the context of graphs, and then a big wall here, and now, oh yeah, but if when I'm looking at a level sets, I've got a totally different story. And so we're going to develop those stories over time, but you need to build that wall now so that you won't conflate them. Okay, so here's that process, the level set construction. So it's another solution set to another equation. The process is you take the values of the function, you set them equal to not a new variable, you set them equal to a constant. Right? And then we're going to look at the set of solutions. Of this equation. You've got this equation here. We're looking for the collection of all points that satisfy that equation. That's a solution set. Okay, so quick observation. Let's look at this equation here. Let's count variables. How many variables are in this equation? Well, when we were talking about graphs, we had, input variables and, m output variables. And so altogether we had n plus m variables, and therefore an n plus m dimensional picture. Not here. Let's count variables in this equation. In this equation, I have only the variables from the domain. This is simply in variables. This picture that we're about to draw will be a picture in the domain, Rn. Okay, so not only are level sets different from graphs, they live in a different world from graphs. Yeah? Okay. All right. We're going to draw some pictures, but I want to talk a little bit about terminology and notation first. So first of all, I'll elaborate on this soon, but you've probably seen some pictures of level sets in the past. And for a pretty good example is when you watch the I don't know if anyone does this anymore, but if you go to I was about to say, if you watch the news and watch the weather, nobody does that anymore, right? But if you go to the appropriate app and pull up a temperature map, right? Then what they will have on there is various lines showing that here's the temperature where it's the 70s, and here's where it's the 60s, and here's where it's the 50s, etc. Those are curves. I'll draw a picture of this in a moment, where they're describing collections of points where the temperature are all the same, and where the temperature is all the same is a level set. So specifically. Heat maps are level sets, and because they are level sets, because they are setting equal to constant a certain function. Now, what is that function they're looking at constant values of? Well, it's temperature. Those curves are sometimes called isotherms. Yeah, anyway, it's terminology. And you'll see this construction applied in other situations. If you're looking at barometric pressure, the level sets are called isobars. And if you are an economist and you're looking at some quantity of interest, and they'll just call them isoquants. So anyway, just be on the watch for that kind of terminology. Next little bit of notation I want to talk about is very conveniently relevant to level sets, and it's the idea of a pre-image. So let me talk through what a pre-image is. Y'all know what an image is. Let me come over here for a second. If you have a domain and a function and a target, I'm just drawing this schematically. momentarily. If you have some value x in the domain, plug that into the function, and out will come some value, some output value f of x, and let's suppose that output value is c. Okay, so the terminology we would make here is that the image of x is c. Okay, so we've talked about image before. It just means outputs. Okay, so pre-image is kind of the opposite of that, but it does have to include, we have to factor in a different consideration, and that is that, look, there may be other points over here that also, when you plug them into the function, also land on the same C. In fact, it might not be just a finite list of points. It could be an entire curve or an entire surface. There could be a lot of points, all of which, for this whatever particular function, that all of which land on C. Okay, so the idea of the term pre-image is not quite going to fit on the. Oh, you know what I can do? Here, let me cheat. Scooch that over there like that. Now I can fit this all on. The idea of pre-image, this notation here, is to say, well, look, image refers to the function. You know, the function f goes that way, right? So let's think about, well, if you're going the other way, if you go backwards, it's as if we're inverting the function. And so the pre-image is the collection of all of the x's. It's, you know, given an output, let's look at all the inputs that land on it. Okay, so this notation, F inverse, I think is pretty plausible. The terminology pre-image, I think, again, pretty plausible from this picture. We're looking at the stuff that comes before the image. The stuff that leads to this image. So anyway, pre-image, pretty natural term. Notice, of course, that a pre-image defined like this, it comes from, in fact, exactly the same equation as a level set. So all level sets are pre-images. So anyway, this is very convenient terminology. Let's see an example now. Here you go. Let's look at this function. We drew a graph of this function in the last section. F of x1 comma x2 is x1 plus x2. Drew a graph. The graph was a plane. The plane was kind of hard to draw. It was going up as it comes out of the page. Right? So so a plane in R3 was the graph of that function. Now let's draw level sets of this function. Okay, level sets are pre-images. It's what we get when we set the value of the function equal to different constants. So if you set it equal to 0, what do you get there? You get a line. So that is the level set where the output value is 0, or said differently, that is the pre-image of 0, or that is F inverse of 0. What if we were to look at the level set where we set the function equal to 1? Now, it's a different constant, right? But still, that gives us a line, and that's a different line. That's this level set or this pre-image, et cetera, et cetera. You could do this for any constant. Notice then that no matter what that constant is, you always get a line for the level set, for the pre-image. Right? And so all of the remaining level sets, well, they're all lines. They're just lines that sort of move and moving up or down, depending on what that constant is. Okay, so what we have here is a picture looking back at our function. That function, the graph was a plane. The level sets are a bunch of lines. It's a very different picture, right? It's not a plane, for one thing. It doesn't even live in R3. It's very dramatically different kind of a picture. Okay, so again, now I've said this before, I'll say it again. you can well imagine that how we use a picture like this to understand a function is going to be pretty significantly different from how we use graphs to understand functions. The calculus of this picture is going to be very different from the calculus of graphs. And in both cases, we can draw certain conclusions about functions. Okay. All right, so let me go back to the weather example. I claim that when you look at the weather app, whichever app you use, no judgment. Here's a quick picture of the U.S. And, you see pictures that look kind of like the following. It's always really hot down here. Ooh, man, I spent time down there in the summer. That's rough. So it's hottest there. And then, poor Arizona. Something like this. And then not as hot, but maybe a little hot in this next zone. And then, not that bad at all. Along in there, perhaps. And then downright comfortable, perhaps. Over here. I'm probably getting this all wrong. I'm probably scientifically way off. It may be cool further north. Okay, so you see a picture like this, right? So where's the level sets? The level sets are where the function is equal to a constant. Now, if they have these labeled as, this is, the 100s, and then they'll label it as, this is the 90s, and this is the 80s, etc. What they're saying then is that this curve right here, this curve is the barrier between the 80s and the 90s. And what value is it that is the barrier between the 80s and 90s? That is where the temperature is exactly 90. So those barrier curves, sort of where the colors meet, those are level sets of the temperature function. Everybody on board? Okay. So, one way to think about level sets. Okay. Let's see here. Here we go. All right. Okay. So now, is there a connection to graphs? And the first and most important thing to remember is that graphs and level sets are not the same thing. Okay. That said, I've said it enough times, but there is a connection between them, and it's a really nice connection. So make the following observation. Suppose I look at the following level set. Here is a level set. Oh, excuse me. I'm sorry. Got ahead of myself. Sorry. Let's look at a graph. That's a graph of a function f. 2 input variables, 1 output variable. That's what the graph looks like, let's say. Now, next question I want to ask is, what happens if I were to take a cross-section where I set z equal to a constant? Okay, well, geometric appeal, but if you have a surface like that, setting z equal to a constant, that's a horizontal cross-section. That's going to give you a slice. That's going to give you some curve, right, that looks like this or something. And what can I say about that curve? Well, that curve, being as it is a cross-section, that curve satisfies both of these equations, and therefore that curve is where, let's see here, well, z is equal to f of xy, but also z is equal to c, and therefore f is equal to c. So this curve here is kind of a level set of the function. So let's say this all out then. Cross sections of graphs give you level sets. That's a pretty strong connection. Cross sections of graphs are level sets. Just to get our, just to see a specific example, here's a function that here's the graph of a function we've seen before. This is z equals f of x comma y. This is a graph of f of xy equals x squared plus y squared. Let me write x squared plus y squared here. So that's the graph of that particular function. And then notice you take this graph, you take cross sections by setting z equal to a constant. You set z equal to a constant, and you are effectively setting f equal to a constant, and you get circles. Circles like that. Of course, now you get smaller circles down there. You get larger circles up the higher up you go, and your level sets are, as I have drawn here, a bunch of concentric circles. Everybody on board? Okay. All right. And then one little quibble, and then we'll call it a day. Oh gosh. Yeah, super quick. A little quibble. Technically, the cross section of the graph is a curve that sits up inside of space in R3. So technically, the cross section of the graph is not exactly the same as the level set. The level set lives in R2. The cross section of the graph lives in R3. Right, but when I say that they're the same, what I mean is if you take that cross section and then throw away the z coordinate, just kind of erase the z coordinate, then in fact you do get the level set. So minor little quibble, but I did feel the need to point that out. Okay, call it a day. See y'all later. I do have homeworks to return.